To introduce this, I'm going to go around kind of the back way and cover a little bit of what we did last week, in a sense, to really kind of ease us into this idea of confidence intervals. Okay, so last week we were discussing the idea of this idea of what samples from a population would look like if we repeatedly took those samples over and over again and calculated the means of each sample and then put that into a distribution to see what the distribution looks like. So if I draw that, here's a population. This is the entire population. It's normally distributed. It's some function, some numeric variable in that population. Let's say it's shoe size. Okay, and I'm going to say that the mean shoe size in this population is 8. So the mean shoe size. Now that's just for the population, so it's a parameter, and I'm using mu to represent it. Mu is equal to 8. Now the standard deviation, the spread of shoe sizes, the standard deviation is equal to, I'm going to make up a number 2. Okay, that represents the standard deviation of the population. So sigma is what I'm using for standard deviation. So the spread here, right, is a mean of 8 is in the middle. 50% of people are below 8, 50% of people above 8, and it's symmetrical, right? But we also know certain things about this population. One of the things that we know is that 95% of this population is going to have a shoe size, assuming it's truly a normal distribution, and this is really its standard deviation, that's going to be between roughly 4 and 12, right? 2 standard deviations below the mean, 2 standard deviations above the mean. That's 95%. Some people are going to have really tiny feet, and some people are going to have big feet, right? And they're going to be on either side of those. Now, I don't know about shoe sizes very much, so don't take this to mean that if you have a shoe size of 12 and a half, that you got big feet, or if you're got a shoe size of 4, you got really tiny feet. I have no idea what the distribution is. Shoe size, I'm just using this as an example. Okay, so now let's imagine this is a large population, maybe it's a population in the entire United States, right? So let's say we have here the population of the entire United States. We will never know what the mean shoe size is for the United States. We'll never really know for sure the standard deviation of shoe sizes. In order to know that, we would have to get the shoe size for every person in the country. For the most part, almost universally, we're never going to know the population mean, the parameter that we really are interested in. That's really what we want to know is the population mean. Right? Sample means they're only limited usefulness. They're a sample of people. We really want to understand what an entire population's mean is, or proportion is, or prevalence is, right? But we never really have access to that, except for maybe a census, or very rarely, right? So that's our problem. So since we're working with samples, we want to really understand how samples work, how samples behave. Okay, so if we have a normal population with a mean of 8 and a standard deviation of 2, if I were to take a sample of size 25, okay, and I would then take this population, take 25 people at random, sample them, find their mean, maybe it's 7. Take another 25 people, sample them, find their mean, maybe it's 9. Take another 25 people, sample them, maybe it's 10, so on and so forth. If I did that many times, say an infinite number of times, if I did that, I would wind up with a new distribution. If I took all those sample means, I would wind up with a new sample distribution, which would look something like this. Okay, and the middle of that distribution would be 8 as well, or very close to 8 anyway. So, which makes sense. If I take a random sample from this population, half the time they'll have an average below 8, half the time an average above 8. So my sample mean, right, is going to be equal to 8. But this is a giant sample. Many samples that have been samples of size 25, means of many samples of size 25 taken from this same population. Well, now the thing about that is that even though I should wind up with a sample mean for all of these different samples of around the same as a population mean, and 50% of the time we'll get under, 50% of the time we'll get over that mean, right? Well, it's unlikely I'll get choose mean sizes that are as small as, say, 4 or as big as 12. Why is that? Because I'm sampling 25 people. The likelihood that all 25 of them are size 4 or smaller is going to be very unlikely, or size 12 or bigger is going to be very unlikely. So we wind up with a narrower distribution. Our mean is the same, right? Our sample means approximate our population mean, but so we expect that to be around 8, but our sample standard deviations of all these means is going to be narrower, and we know that it's going to be equal to the standard deviation of the population, sigma, divided by the square root of the sample size. Okay, or in other words, in this case, 2 divided by the square root of 25, which is 5, so our standard deviation is going to be equal to 0.4. Okay, so what does that mean? That means that 95% of the time, when we take a sample from this population, we would expect our sample mean to be between 2 standard deviations below 7.2 and 2 standard deviations above the mean of the population, 8.8, right? So everybody agree with that so far? Are you guys okay with that so far? It makes sense to you? 95% of the time, if I take a sample of size 25 from this population, 95% of the time that the result will be a sample mean between 7.2 and 8.8. That's just the way that random samples work. Now, what would happen if I take a sample of size 100? Well, naturally, size 100, well, we would expect all of those sample means to be even closer to the mean than, say, when we took a sample size 25. So we'd expect to see something like this, right? Again, the mean of all the samples that we took would again be 8, but the standard deviation of all the sample means is going to be equal to standard deviation over the square root of n, which is going to be equal to 2 over the square root of 100, which is going to be equal to 2 over 10, which is going to be equal to 0.2. So 95% of the time, we would expect to get a sample mean from this population, if we took a sample of 100, somewhere between 7.6 and 8.4, right? So our spread for likely results, in other words, 95% of the time being likely results for sample sizes, our spread as our sample size goes up becomes narrower. That's the sigma. That's sigma. That sigma is the population standard deviation. Okay, in other words, the standard deviation of the sample means is equal to the population standard deviation divided by the square root of the sample size, right? So that's where we're getting that. Keep in mind now, we're never going to know what this is, and we're never going to know what this is. So we're speculating quite a bit here so far, right? In a moment, we're going to start to work on things that are going to put this in perspective in terms of the real world. Okay, so now I'm going to give you a situation now where it's a little bit more of a real world kind of thing. Okay, so I'm going to say, let's say I'm now going to be looking at the weights of gerbils in grams. Okay, let's say the average gerbil, we take a sample of size 100, right? And I tell you that the standard deviation for, let's say we've done some other study somewhere. We found some other study where they sampled many thousands and thousands of gerbils. And for some reason, we're pretty confident that the population standard deviation for gerbil weight is equal to 50 grams. Okay. Now, let's say we have a population of gerbils that, that are slightly different. They're a different breed of gerbils, but we think that the variability in weights is the same as all our other gerbils, right? Let's say that I want to know what the mean what the mean weight for that new population of gerbils is. Okay, and I'm willing to assume that we know the standard deviation from previous studies. Let's say I take a sample of size 100 from that population, from this new population, and it turns out that my mean for my sample of size 100 is equal to, I'm going to say 300 grams. Okay, so now I know what my mean for my sample is, but I don't know what my population mean is for this new population. All I know is my sample mean. Well, it's really nice to know the sample mean. Now I can go and tell someone, well, I randomly sampled 100 gerbils and I found an average weight of 300 grams. So I'm gonna, I think I know roughly what the average weight of these gerbils are, probably around 300 grams. Well, wouldn't it be nice if we knew, if we could express with better precision how well we know the weight of those gerbils? Okay, well, what's going to happen here is now we're going to take this information that we have. We're going to say to ourselves, okay, let's take a look at how we would expect population, if this were the mean for this population, how we would expect those gerbils to be distributed. So if the mean were really 300 and the standard deviation was 50, well, with a sample size of 100, right, we would expect the standard deviation of all of these, of repeated samples from this population, we would expect that standard deviation to be equal to the standard deviation of the population over the square root of the sample size. We'd expect that to be 50 grams over 100, square root of 100 is 10. We'd expect that standard deviation to be 5. So say 300, and two standard deviations below would be 290. Two standard deviations above would be 310. And I would say, well, I would expect if I took repeated samples and the mean were really 300, I would expect that 95% of the time I would get a sample mean, if I sampled 100 gerbils, between 290 and 310. Well, the problem here is I don't know the true population mean, do I? I only know what my sample is, right? My sample was 300 grams. Okay, so we can't use this to really say what this spread would be like around 300, but we can use it a different way. Okay, we can say to ourselves, well, I don't really know what the population mean is, but if I took samples over and over again, I would have gotten, and this would mean this is what I would have gotten. I can't really use it that way, but let me use this a different way. Let me say instead that I'm 95% confident that the true mean, mu, is between 290 and 310, right? So I can use what I understand about the way populations are distributed to quantify how likely it is that I really know the population mean. Okay, so I could say 95% of the time, my true population mean between 290 and 310. Well, wait a second. That's only because I went 2 standard deviations below and 2 standard deviations above, right? What if I went 3 standard deviations above and below? Well, that would be 285, and that would be 315. I could say with 99% confidence that my true population mean is between 285 and 315. Another standard deviation to the left and to the right. Well, doesn't that kind of make sense? If I'm willing to spread out my range, then I can be more confident that I actually caught the true population mean. If I want to pick a narrower range, right? If I want a narrower range, then I can say I can only be less confident. There's a higher chance that I will miss the true population mean within that interval. Okay, so this is what we were looking at before. When we calculate a confidence interval using population standard deviation and a sample mean, if we try and calculate a confidence interval, well, if we use a 95% confidence interval, like in other words, 2 standard deviations to the left and to the right, now you and I know that that's really 1.96. right? We got this from the empirical formula, but it's really 1.96 if we look it up on the Z table. If I'm willing to look 2 standard deviations or 1.96 below the mean and 1.96 above the mean, then I can get a range where I'm 95% sure the true population mean is located. Well, what does that mean? That means if I did this 20 times, right? Most of the time, I would wind up with a range. Here's a true population mean with a range that actually captures the true population mean. But at least one time, most likely one time, I'll miss it, high or low, one way or the other. I'll miss it one time, right, out of 20. If I did it 100 times, I'd capture the population mean 95% of the time, but I would miss it 5% of the time. So we're never really 100% sure that we've captured the population mean, because our sample size would have to be so big to be 100% sure that it pretty much you get into a meaningless range. It would be almost like not why even bother, like taking a sample if you're gonna look for that wider range. So I'm gonna stop for a moment. Does that make sense to you guys so far? Are you starting to get an idea of why we're interested in confidence intervals? We're interested in confidence intervals because when we take a sample, they'll help us understand how well we know what the real true population mean is. And we can monkey with our level of confidence if we want a narrower range or a wider range. Okay, if we're willing to be less confident, we can afford a wider range. If we want to be more confident, we need a narrower range. So now I'm going to I'm going to try an example, kind of a real world example of something that we might be interested in doing. I'm going to go on to Blackboard. We have an exercise on Blackboard, and I'm hoping the first one will be something that will make some sense for this. Okay, okay. Here's now I mentioned up here you can use. We're going to be using the Z table and something called the T table. For right now, we're going to use the Z table, and we're going to talk about that and what I mean by that, the T table, in a moment. Okay, a sample of size 100 has a mean of 160. Assuming the population is normally distributed with a population, I'm going to put that in there just to make it clear. We know the population standard deviation. Is this kind of an artificial situation? Well, yeah, but for the moment, that's the way we're going to deal with it. We know that the sample size is 100. We've taken a sample size of 100. We have a mean of 160. And our population standard deviation, what we call sigma, is equal to 30. Okay? Compute a 95% confidence interval for the mean of the population. That's going to be mu, right? We want to calculate what mu is. We know what x bar is, but then we want to calculate what mu is. So I'm going to go in here and I'm going to say, let's see. Okay, let me take these numbers I have, and I have my sample size is equal to 100. My x bar is equal to 160. And my standard deviation of my population, now x bar is my sample size. Sigma is my population standard deviation, which I happen to know is 30. Again, a little bit of a construct. Occasionally you have a pretty good idea of what it is because someone else has done like a big study that involved thousands of people instead of 100 people or something like that. So I've calculated my mean for this sample is 160. Well, how well do I know what the population mean? What is mu? Mu is what we're really after here. Mu is what our ultimate goal is. So the way we're going to calculate what mu is we're going to calculate a confidence interval. And the first confidence interval we're going to calculate is a 95% confidence interval. I want to be 95% certain that I have a range from here to there. I have a range that I'm 95% sure the true population mean resides within. Okay, so how am I going to calculate that? Well, I'm going to calculate that by starting with x bar, and then I'm going to add and subtract 2 standard deviations below the mean and 2 standard deviations above the mean to calculate what my 95% confidence interval. If I do that as a formula, it looks something like this. Plus or minus, add and subtract because you want to go both directions, my z-score for 95% certainty times my standard deviation of the population. How much z, in other words, just like we did before, two times the standard deviation, 2 times 30 in this case, right? Well, hang on a second. 2 times actually my standard deviation, right? Now, there's a little bit of an issue here now. We're doing this for a sample, right? So our standard deviation, our mean, is going to be based on our population. It's going to be based on our sample size, right? Sample size bigger, then this is going to be narrow. We're really looking at the standard deviation we're looking at is the standard deviation for our samples of size 100. That's the range that we want to look at. Okay, so let's take a look at it. This is going to be x bar plus or minus z, which is equal to 1.96, right? Remember, for 95% confident, 95% distribute of the population distribution or sample confidence and so on, it's really 1.96, not 2.0. We get from the z table, okay, times sigma over the square root of n. Okay, so the bigger the sample size is, the smaller this number is. The smaller we add and subtract from x bar, which changes our range for our confidence, makes it narrower or wider. So what's making it narrower or wider? Sigma is, but also our sample size is. So what is our standard deviation? Our standard deviation for our sample of that size is going to be equal to sigma over the square root of n. That's going to be equal to 30 over the square root of 100, which is 10. So standard deviation is equal to 3. So it's going to be x bar, which is 160, population mean, plus or minus 1.96 times 3, our standard deviation for our sample means. Okay, so now let's see, what do we wind up here? We wind up with 160 plus or minus 1.96 times 3. I'll get my calculator up here. 1.96 times 3 is equal to 5.9. I'm going to call it 5.9, make things a little simpler for us right now. 5.9, right? So 160 minus 5.9 is going to be 154.1. And 160 plus 1.9 is going to be 165.9. So we are 95% confident that the true population mean, mu, lies between 154.1 and 165.9. Let's say I want to be more confident than that. Let's say actually I'm going to go the opposite first. Okay, this is 95% confidence interval. Let's say I'm willing to be 90% confident, right? Instead of 9, I'm willing to be a little less confident because I want a wider range, right? I'll take a look. I'm willing to be a little less confident. Okay, so now how would we calculate that? Well, it's going to be 160 plus or minus. Well, our distribution, our sample distribution, our population distributions, in order to get 90%, we use a smaller z-score. Anybody remember what the z-score was for 90% on our z table? Let me open it up. Okay, so let me close this. Let's look it up here. Let's look it up. So if I want to know, 90% would be 5% on either side, the left side or the right tail. Left side 5%, right side line 5% would leave 90% in the middle, right? So I'm looking for an area which represents 5%. Okay, so 5% looks like it's around here, 1.6. I'm going to call it 6.4. It's really between these two numbers. I'm going to call it 1.64. Okay, so I'm going to call that number 1.64. So the number of standard deviations above and below that I need to go for a 90% confidence interval is 1.64. Okay, times my standard error again, which is 3, right? Sigma over the square root of the sample size. It would have been even a smaller number for a bigger sample, right? So what is that going to be? Let's calculate that. Oops, lost my calculator there somewhere. Where'd it go? Must be behind something here. Come on, calculator. Maybe I need to close it and then open it again. Let me quit the calculator and open it again, and it should pop open where I can see it. And I still can't see it. Anybody want to calculate that for me? I guess I could bite the bullet and just use my fingers on my phone here or something. 4.92. Thank you very much. I appreciate it. Okay. So that's 160 plus or minus 4.92, right? So I'm going to call that 4.9. So that's going to be equal to, let's see, minus 160 minus is going to be 155.1 up to, add that, 164.9. Notice it's a narrower range than our confidence interval here, so 95%. Why is it a narrower range? Because we're willing to have less confidence. So I'm going to try this again for a 99% confidence interval. Okay, for 99%, it's going to be 160 plus or minus, well, let's take a look at what z-score we have to use in order to calculate that again. Okay, here we are. So in this case, what am I going to have on each side for the middle 99% to be here? What percentage can be in the lower tail and the upper tail? Well, there's 1% left, so there can only be half of 1% in each one of these tails. 0.005, 0.005 looks like it's gonna be around 2.5. Looks like it's around here. I'm going to call it negative 2.58, and it would be positive 2.58 on the top end there. So it's 2.58 is going to be our z-score. Okay, now, if you just remember those numbers now, 2.58, right, times our standard error, which is 3. Okay, whoops, I got ahead of myself there a little bit. Times our standard deviation for the sample means is 3. Okay, so it's 2.58 times 3. Can somebody calculate that for me, since I'm calculator deprived here? Okay, 7.74. Okay, so it's 160 plus or minus 7.74. I'm going to call that 7.7 for argument's sake for right now. Okay, so that's going to be, wow, it's going to be quite a bit different. Now, is my confidence interval going to be, for 99% confidence, going to be wider or narrower? Make your prediction. Is our 99% confidence interval going to be wider than 95 or narrower than 95? It's going to be wider. Makes sense, because we need a wider interval in order for us to have a lot higher confidence that we actually captured what mu was. And in this case, it comes out to 152.3 and 167.7. Okay, that's our 95% confidence interval. Now, I gave away a couple of terms that I haven't decided, that I accidentally gave away at least one of a couple of terms that I haven't defined yet. This number, which is the standard deviation of the population means for that particular sample size, that number, instead of calling it standard deviation of the population of the sample means, we call it the standard error. Okay, that's called a standard error. So really our formula is Z times the standard error. The other thing, a term that I didn't define yet, was this amount that we're adding and subtracting to the population mean is called the margin of error. Makes sense, right? Because you're adding and then subtracting. It's the margin of error. How much below, how much above. So standard error and margin of error. Now I'm going to take a quick look. See, we got a question here. Can you explain the wider, narrower confidence interval? Okay, so the wider, basically what we're giving here is a range that if we take a sample, right? We take any sample we want, sample size of 25, sample size of 100. We are calculating a range within which we think the true population mean resides. We're basing that on knowing from our sample. Let's say we take a sample of size 25 and we get a sample mean of 50, right? Our sample size 25, our sample mean is 50. Well, that's our sample mean. We're not interested in the sample mean. We're interested in what the population mean is. So our sample mean is 50. But if we know something about the way that the population is distributed, in other words, the spread of the population, the standard deviation, well, then we can take advantage of knowing the sample mean and the standard deviation to predict a range within which we would expect to find the sample mean. It may not be 50, it may be 48, between 48 and 52. It may not be 50, it might be between 45 and 55. But depending on what the standard deviation is and what level of confidence that we at, we want, that is what our confidence interval represents. The larger the sample size is, the narrower our confidence in it is. We're more confident that we're going to capture the mean within a narrow range. So as the sample size goes up, our confidence interval gets narrower. As our confidence level, say 95, 90, 95, 99, 90, as our confidence level goes up, the width of the confidence interval goes down, right? If we want to have a high level of confidence, we need a wide range, right? To say that we know it with 95% certainty it's between those two numbers. Down here, it's going to be higher than it is up here. So the width of the confidence interval, so big sample size helps us get a narrower range, and a lower level of confidence helps us get a narrower range because we can afford to be less certain. Okay, so they kind of fight against each other a little bit. 90% confidence between how likely is that? It's incorrect. Okay, well, it doesn't. The reason why your confidence interval is between 100 and 101, that was determined by your sample size and your standard deviation. Okay, so if I say that I have 90% confidence that the true population mean is between those two numbers, that's literally what we mean. In other words, there's 10% chance that it's different. It's not between those two numbers. So if I were to say we're 95% confident that it's between those two numbers, then then it's similar. You would say that, gee, there's 5% chance I could be wrong, that it's not there. But that's really determined by those numbers, okay, and by what you choose as your z-score. Okay, so you can decide how confident you need to be. And we got a higher range as the confidence interval increased. Okay, as the confidence interval increased, in other words, we want it to be 99% sure. Well, in order to be 99% sure, I need a wider range. In other words, in this case, I'll give you an example. If you want to guess my weight, please don't, by the way. Okay, you have on nobody. I don't want to see anybody guessing my weight in the chat box. Thank you. Okay, if you were to guess my weight, right? If you said, well, I think his weight is between 100 and 300 pounds, you could be 99.99% sure. You could have a confidence interval of 99.99%. Because it's almost definitely in that range. But how useful a range is that? 100 to 300 pounds. Now, if you were to say that my weight, now I'm making up numbers here, my weight is between 180 and 200 pounds, well, you might only be 95% sure that you've captured my weight. The wider range that you use, the higher your confidence is. So the higher that confidence percentage is. The narrower range that you use, the lower your confidence. So a 90% confidence interval is going to be a narrower range than a 95, which is going to be a narrower range than the 99. Wider the interval is, the more confident that you are that you captured the mean. That's really what confidence interval is. It's your prediction of the mean is between these 2 points. Does that make sense? Ghislaine, does that make sense to you? Okay, good. So let's try a couple of examples here. Let's move on, see if we can try another example. Okay, okay. If it said population mean where it would be 160, no, to be I don't want. Okay, we don't need that. Let's. After observing 25 randomly selected caseworkers, the supervisor noticed that the average number of cases carried by each worker in a week was 50. So X bar 25 sample was 25. X bar 50 is the average number of cases carried by each of those by 25 caseworkers. From previous long-term observations, it is known that the standard deviation for the entire department, in other words, sigma, again, we don't really know that, but we're making believe we know that here, is 9. Sigma is equal to 9, standard deviation of the population. So what do we know here? I'm going to go back here. And what we know here is we know n, right? N, the sample size is 25. We know X bar, the average number of cases that each worker carried in a week was 50. And we know sigma, the population standard deviation, is equal to 9. So the question is calculate the 95% confidence interval for the mean number of cases per worker per week that the entire department carries. Okay, so we're not gonna go back and find the entire, find out how many cases the entire department carried. Might be 1,000 workers or something like that. We're just going to randomly sample 25. But we want to know what mu is, not X bar, but what mu is for the entire department. Okay, well, we're interested in knowing that with a level of confidence of 95%. We want to be 95% sure that we know what that the true population mean mu is within the numbers that we get. Okay, so how are we going to calculate that? Well, X bar plus or minus the Z score for 95% confidence, right, times the standard error. Okay, now the standard error, what is standard error equal to? The standard error is equal to sigma over the square root of n. That standard error is the standard deviation of samples of size 25 with that mean. Okay, so that's going to be equal to 25 divided, 9, divided by the square root of the sample size. Sample size is 25, squared sample size is 5, so that's going to be equal to 1.8. Standard error is equal to 1.8 cases. Okay, so let's see what we got here. We've got X bar is 50 plus or minus Z for 95% confidence, 1.95 times the standard error, which is 1.8. Okay, so what do we wind up with there? 50 plus or minus 1.95, 1.96. 1.96. You guys can catch me on that stuff, right? Times 1.8. Okay, that's the Z-score for 95%. Okay, so what is that going to be equal to? Okay, let's see if I can get my calculator up. If not, you guys might be ahead of me. Good work. 3.5. I'm going to call that 3.5. Okay, so so it's going to be equal to 50 plus or minus 3.5, right? So, and that's going to be equal to our confidence interval. First of all, what's this number 3.5 called? We know that this 1.8 is the standard error, right? Standard deviation of the samples, right? What's this number 3.5 called? I'm going to add and subtract. Margin of error. Very good. Excellent. Okay, so that's going to be equal to 46.5 when I subtract that, and it's going to be equal to 53.5 when I add it. So I am 95% sure that the true population mean for all of the workers in that department is between 46.5 and 53.5 cases per week. Okay, so that's my 95% confidence interval. Now let's try calculating. Let's say I want to be more confident that I really captured it. I want to be 99% sure that I really captured between these two numbers the population mean. So I'm going to try a 95, 99% confidence interval. So anybody, first of all, is it going to be wider than this or is it going to be narrower than this? It's got to be wider, right? Makes sense. It's got to be wider. And you want to be more confident, you need a wider margin to make sure you capture it. So actually, even if you don't remember that, it's going to work out that way because this time we're going to use X bar plus or minus the z-score for 99% this time times the standard error. And we know that the z-score, excuse me, I'll put in 50 here. We know that the z-score for 99% is 2.58. Why do I remember that? Because we looked it up before, but also because we're going forward, we're going to remember 99% confidence interval, z-score is 2.58, 95% confidence interval, z-score is 1.96, and a 90% confidence interval, the z-score is 1.64. Why are we going to remember it? Because we're going to use it so often that it's going to be kind of burned into our heads by the time we get out of this course, right? So that's going to certainly burn into my head, let me tell you. So at any rate, those are the numbers we're going to be using. If you forget them, you can just go back to the table and look them up. So it's going to be 2.58 times 1.8. So just because that z-score is larger now for a higher level of confidence, that's automatically going to be making our margin of error a bigger number, which means that it's going to be a wider interval. So what do we got there? Anybody calculate that? Plus or minus 4.64. I'm going to call it 4.6. Okay, so I can do this easily without a calculator. And so this is going to be equal to, instead of 3.5, margin of error is 4.6. So it's going to be equal to 45.4 and 54.6. And again, if I'm going to do a 90% confidence interval, that's going to be narrower. Why is it going to be narrower? Because we're going to use 1.96 to calculate our margin of error. Smaller number, smaller amount we're going to add and subtract. It's going to be a narrower range, but because it's a narrower range, it means we're less confident. Okay, so I want to go over one other possibility that you're going to run into, and we're going to be talking more about this when we get into the other stuff next week, as we move on with this stuff, and that's when you deal with a prevalence or a proportion. Now, let's say that I were to tell you that I sampled 100 people, and I found that out of those 100 people, 14, I'm going to make a bigger number, 15 of those people were smokers. Okay, so what is, and 85 people were not smokers. Okay, so what is my proportion of smokers? Now, mu and p, those are parameters, right? Those are population proportions. And they're also called point values. Mu is a number, right? Mu is 20. Mu is 80. Proportion is 20% or 14% or 5%, right? That's a number. Those are called point estimates, right? So it happens that these are point estimates, point values, and they are parameters. Okay, but now when I'm talking about a sample, 100 people, 15 smokers, 85 not, well, what's the proportion of people in this population that are smokers? Well, I'm going to call that, just like before, when I was dealing with a sample mean, I called it X bar instead of calling it mu. So I knew it was a sample mean. Well, since I'm working with a sample proportion, I'm going to call this P cap, like that. Okay, so when you see P cap, you know I'm talking about a sample proportion. What is P cap equal to? It's equal to 15 smokers out of 100. So the proportion of smokers, or prevalence, if you want to use that word, is 0.15. Okay. So now I'm in the same fix now that I was in before. I'm saying that based on my sample of 100 people, I'm saying that, gee, based on that sample of 100 people, I'm saying that I think that the percentage of people that are smokers in this population is 15%. Remember, I'm really interested in the true population proportion, not p cap. I'm just using p cap to get to an end, right? So that's really what I want. But this is what I know. So I'll never know this. So at least maybe I can understand how certain I am of what that is. That p cap is based on the sample size that I took. Well, I'm going to do exactly the same thing I did before, except this time my standard deviation, or my standard error in this case, because it's a sample, you could call it standard error, is going to be equal to, and you notice this formula before, the square root of p times 1 minus p over n, the sample size. This actually, I should draw that so it's clear everything is under that square root. Okay, so if I want to calculate a confidence interval for my true population proportion of people that smoke in its population, it's going to be equal to, let's see, it's going to be equal to p cap plus or minus, well, since I want to know, let's say I want to know if 95% confidence interval. Well, this is going to be, I'm assuming that this distribution, random distribution of samples that I took over and over again, a size sample, size 100 from this population, is going to be normally distributed around p cap, a little, half above, half below, whatever, above, half above and half above p rather. Okay, I'm going to say p cap plus or minus the z-score that I need for a 95% confidence interval. Sometimes you'll see that a little bit differently. Alpha is equal, alpha over 2 is equal to 0.025. Don't worry about that. Just keep in mind this is for a 95% confidence interval. I don't want to confuse you, so I'm going to stick with that for now. Okay, z-score that I need for a 95% confidence interval times my standard error. Okay, so let's calculate these for this case. So 0.15 plus or minus the z-score that I need for a 95% confidence interval, which is 1.96, times my standard error. What's my standard error? It's going to be equal to the square root of 0.15 times 0.85 over 100. So you got to resolve this and then take the square root of it. And I really wish I could get to my calculator. Why can't I see it? Where is it? It's not down there. I think you should be able to, maybe I can do this and see. Whoops. That's not what I wanted to do. Ah, there it is. Okay. Whoops. Oh, I see. It's behind my, you guys can see it. I couldn't see it. I have a control panel that's up here that you guys can't see. So you're probably sitting there wondering, why can't this guy see this thing? Oh, good. Excellent. Somebody worked it out already. Okay. So that's the standard error, right? Standard error is, is that the standard error you calculated, or is, yeah, 0.001, I'm going to call it 3. So it's going to be 1.96 times 0.0013. Okay, so anybody want to calculate what that is? Okay, so it's going to be 0.15 plus or minus, okay, 1.96 times that. I presume that was the standard error, not the, I lost it again. Here we go. I'm going to do it on my own this time. Okay, 1.96 times 0.0013 is equal to, I think I made a mistake there. Did I make a mistake there? What standard error? 0.85. It's p times 1 minus p. In other words, the proportion is 15%. 1 minus p is 0.85. That's a 0.85. Yeah, I didn't put it in parentheses there, did I? Right, so that could be a little confusing. It's 0.85. Right, that's over there. 0.15 times 0.85. Actually, I think, hang on a second here. Something's wrong here. I think you guys might have got this wrong here, believe it or not. Oops, I think I must close my calculator now. There's got to be a better way to do this with these silly machines. 0.15 times 0.85, right, divided by 100 equals 0.0125. Now I got to take the square root of it. The square root of it, whoops, excuse me, square root of that is 0.035, 0.036, I'm going to call it. So this is equal to 0.036. 0.036. So now it's 15 plus or minus 1.96 times 0.036. So that's I'm gonna roughly call this 2. So this is gonna come out to be roughly 0.07. So it's 0.15 plus or minus 0.07. Okay, so that's going to be equal to 0.08, comma 0.22. Okay, so I am 95% certain that the true population proportion that is between 0.08 and 0.22. And barring a problem with my math, I think I'm right there, right? You guys agree with me? It looks like somebody else got the same standard error. We're going to basically double that, 1.96 times that. That's 0.07. So that is my range of confidence, my 95% confidence range. I'm 90. Yeah, oops is right. 90. You trust me. You've seen me do plenty oops myself, and I'll do plenty more. So our 95% confidence range is 0.08 to 0.22. Well, how could we improve that? How could we make that a narrower range? Well, I can make it a narrower range by reducing my level of confidence to 90%, right? Because that would change that 1.96. It would change that to 1.64, would make it a narrow range. Or I could go to 99% and make it a wider range even than that is, right? But the other thing I could do is increase my sample size. Instead of taking a sample size of 100, I could take a sample size of 1,000. Okay, so if I took a sample size of 1,000, that n would be very big on the bottom there. My standard error would be smaller, and my margin of error would be smaller. So sample size has a lot to do with this, doesn't it? Variability and sample size have a lot to do with this. Of course, if I wanted to know my 99% confidence interval, the only difference here would be this would be 2.58. If I want to know my 90% confidence interval, the only difference here is that this is 1.64. Now, you may have remembered that Professor Cassia mentioned, Professor Pica mentioned that the range here that we're working with, right? That when we're dealing with proportions, this whole thing is very dependent on having a very large sample size. What we've done is we kind of take something that's really not really a normal distribution. Maybe it's more like a binomial distribution, special case, right? And you really need to calculate the real possibilities. Like if you remember all those the exponential formulas we had for the binomial distribution, to really calculate it gets very complicated. So our assumption that this is a normal distribution, our way that we calculate our standard error, right? That works great if you have a very large sample size, right? It tends to work pretty well. Okay, so we need a large sample size. I'd say 100 or bigger. Even bigger would be even better. The other thing that we have, the other rule that we have, is that we can't have either side of this, the successes, the smokers, versus the non-smokers being less than 5. So 100 times, what did we say was 0.15, right? 100 times 0.15 is 15. So our n times p is 15. That's greater than 5. Our n minus 1, 0.85 times 100 is 85 people. Our 85 people is greater than 5. So these two, both of these have to be greater than 5. And our sample size has to be large. Maybe a good minimum sample size might be 100. Sometimes you'll see situations where people say maybe it's a little bit smaller sample size is better. But problem with a smaller sample size is it starts to introduce, since we don't really know the real standard error, right? We're guessing at it for a lot of reasons. Okay, it introduces a bunch of error. Okay, so that's a couple of rules that we want there. Now, just to close out, the last thing I want to introduce is something that we'll go on in more detail with, and that is the problem that now I may tell you what my sample size is. Sample size is 100. I may tell you what my mean was from the sample that I took. Sample mean was 200. And now I don't know what the population standard, really in most cases, I don't know what the population standard deviation is. So how am I going to calculate my standard deviation, right? How am I going to estimate my sigma? The only thing I know is the 100 people that I sampled at random, right? So I have to calculate my standard deviation based on these 100 people. So the standard deviation I'm going to use is based on my sample. So my standard deviation of my sample, let's say it comes out to be 20. Okay. Problem here is that, gee, my standard deviation is 20, but I don't know how close is that to the real population standard deviation. Well, I don't know. I might have just been unlucky and picked 100 people where the variability was much wider or much narrower than the population standard deviation. It introduces an extra level of uncertainty in this whole thing, right? So the deal here is that I have to make up for that extra level of uncertainty. So when I go to calculate my 95% confidence interval based on this information, right? I'm going to do it just as I was going to do it before. X bar plus or minus the z-score I need for 95% confident times my standard error. Okay, my standard error, I'm going to calculate that based on my standard deviation of my sample, which I know is problematic. It's not really sigma over the square root of the sample size, which is 10. My standard error is equal to 2. Again, it's shakier than if I had known what sigma was, right? So I'm going to use that 2. So X bar is going to be 100, right? Plus or minus the z-score I need for 95% confidence times my standard error. Okay, my standard error is 2. My z-score, well, here's my chance to make up for that level of uncertainty. My z-score, if I had, I'm going to change this. No, I'm not going to change. My z-score, if I knew my standard deviation, I would have used 1.96 here. But since I don't know my z-score, I am going to use a different table. I'm going to use something called the t-table. And a t-table gives us distributions for which we have less certainty than we do with the normal distribution. So I'm going to open this up at Rusty t-table. And one of you had a question about degrees of freedom before. The degrees of freedom are basically the sample size minus 1. So if I have a sample size of 100, the degrees of freedom are 99. If a sample size of 25, degrees of freedom is 24. Okay, one of the ways you can kind of look at that is that if I have one number, if I have a sample of size 1, then I only have a number. I don't have any degrees of freedom. It can only be that number. If I have a sample size of 2, I have 1 degree of freedom. I have that number or that number, 3 and 2 degrees, and so on. Right? You can kind of look at it that way. It's a little more complicated, really, but you can kind of look at it that way. Okay, so a sample size of 99. Oh my goodness, what happened there? I think my t-table is corrupted here. Oh no, yeah, look at that. That's ugly. Jeez. You know what I'm going to do here? I wanted to do it anyway. I'm going to make this 25. Sample size of 25. Standard error is equal to 20 over 5 is equal to 4. Right? That's the only change there. So I just changed my sample size. Everything else looks pretty good. This is a 4 now here. Okay, so now I should be able to read my table. So I'm going to go here to my t-table. And I'm going to look for a confidence interval of 95%. In other words, 2.5% in that tail and 2.5% in the other tail. But you can see the column here represents confidence interval of 95%. The degrees of freedom here represent the sample size minus 1. So a sample size of 24, and the sample size of 25, degrees of freedom is 24. If I go over to that middle column, I have a t-score of 2.064. Instead of using 1.96, I can use 2.060. And since that's a bigger number, it's going to make up for it's going to make a wider confidence interval, bigger margin of error, wider confidence interval makes up for the uncertainty that's been introduced by my using the sample standard deviation instead of knowing the population standard deviation. Had our sample size been 10, we would have used 2.22. And so on and so forth. And you'll notice also that we also have values for t distribution for a 90% confidence interval and for a 99% confidence interval that similarly do the same thing. Well, look what happens as you get larger sample sizes. As you get larger sample sizes, right, what happens as the sample size goes up? Notice for a 95% confidence interval that the t-value goes down and down and down and down until eventually, for a very large sample, it's 1.96. Okay, it's the z-score, basically, for an infinitely large sample. In fact, long before you get to 1.96, the difference is like 1.99, 1.98, 1.97. It's so close to 1.96 that for large samples, like a sample of size 100, you would be tempted to just use 1.96. If the sample size, but sample size 25, pretty small sample size. So we should really use the t-score instead of the z-score here. So I'm going to get to your questions in a second. I just want to break my chain of thought here. Plus or minus my z-score, which is 2.064 times 4, right? And our 95% confidence interval is going to be 4 times this is going to be 100 plus or minus 8.3. I'm going to call it 8.35 just to be roughly somewhere. I'm going to call it 8.4 just so I can do this quickly. And this is going to be 92.6, 91.6, and 108.4. If I round it to that, roughly round it that. So that's my 95% confidence interval, 95. And the reason why we did this is because we used the t-score. And why did we use the t-score? We used the t-score because it was a small sample size, and we did not know the population standard deviation. Okay, so questions. Why the t-table? We use the t-table when we don't know the population standard deviation and we're working with a small sample size. When to use the t-table, depending on sample size. Well, I've some classes in previous, if you asked me that 10 years ago, I've been adjuncting way too long. If you asked me that 10 or 15 or 20, 18 years ago, back in those days, we used to say, oh, if sample size is over 30, just use 1.96. More recently, real statisticians would probably say, always use the t-table, right? Or if you're a little bit tolerant, you might say maybe a big enough sample size to not use the t-table might be, say, larger than 100 or something like that. So sample size is less than 100. Now, I'm going to show you one more thing, and then I'm absolutely positively going to sign off and give you guys a break for the rest of the night. We've gone on actually a bit longer than I had planned. But I wanted to show you one more thing, and that is that you can calculate confidence intervals on SPSS. Take a moment for it to start up. So this stuff, if you break it down to its basics and just take a look, for starters, sometimes you can gain an understanding of this a little bit better by doing something practical with it. Uh-oh. That's not good news, right? Stop working when? It's not installed. Soon. Okay, soon is bad. Okay, I'll have to do something about that. Good. Let's see if I got the other window open. Yeah, actually, I want to open a different file. Open. I want to open a good file here. Interesting file. I'm going to open this North Carolina birth data set, and I'm going to calculate a mean here. So I need a numerical variable. I'm going to take the mother's age. I'm going to assume that that's normally distributed. And better yet, let's take the mean age of the baby in ounces. Okay, so this is mean age of the baby in ounces, T ounces. Okay, so I want to calculate the mean for all 800 of these mothers. This sample size of 800. So I'm going to analyze descriptive statistics. I'm going to go into descriptives. I'm going to pick out the weight of the child in ounces, move it into my variables box, and ask it to tell me, all I really need is the mean, right? Standard error, blah, blah, blah. Oh, it calculates standard error. What do you know? But for right now, the mean. So what's the mean? Here comes our output table. And the mean weight of babies in this study, born to these 800 sample of 800 mothers, is 1.16. Okay, wow, that's really interesting, 1.16. But you want to know something? How well do I know that? How close am I to the real number? Give me I want a confidence interval for that number 1.16. If I'm going to publish a study, as you saw in the abstract of the study that we looked at earlier, when somebody says, hey, this is the mean, people want to know, well, what's your confidence? What's your level of confidence that that's the mean? So they expect to see next to that mean or proportion, they expect to see a confidence interval so they can understand how likely it is that you really have that's really the mean. Okay, so I'm going to go back here and I'm going to say this time analyze descriptive statistics. Except this time I got to go down to explore. It's going to do descriptive statistics again, except this time it's going to do it. It's going to give me some extra values. So I'm going to say weight of child in ounces, and I'm going to ask it to calculate for me descriptives, including the confidence interval for 95%. I could actually change that to 99 if I want, right? I don't need that. Okay, so I'm going to click continue for 95%. I'm going to click OK, and it will calculate for me here we go. Where is it? There it is. The mean is, as we saw before, 116.38, except this time it gives me a 95% confidence interval, where 95% showed a true mean of all the births in North Carolina that year were between 114 and 118 pounds. That's the value of that. How did it calculate that? It did not use 1.96. It used the t-score for a sample size with 799 degrees of freedom. And we don't have a t-table like that, do we? Well, the thing with SPSS is that it says, yeah, it's a computer program. It can be, it's not extra work for it to be extra precise. It has a t-table, an infinite t-table. If the sample size were infinite, it would use 1.96. But short of it being infinite, it's going to use the t-score instead of using the z-score to calculate the confidence interval. Okay, so if you were to do this and use 1.96, your numbers using the same standard error, why don't we do that? Let's give that a try. I wonder if what I'm saying, I probably shouldn't do this because it could make a liar out of me. But let's give this a try. Clear memory. Okay, so our standard error is 7.79. 0.797 times 1.96. 1.96. This is our margin of error. I'm going to put that into memory. And I'm going to clear this. Now I'm going to take our mean, which is 116.38, and I'm going to subtract our margin of error, and we get 114.81. We actually get 114.82, right, instead of 8.1, because it rounds up. But you can see there's a tiny little bit of difference, because only tiny difference because the sample size is so enormous. 800 is a really big sample size. But we did get a different, we got 8.2 instead of 8.1. We did get a different answer than we would have gotten if we used a z-score of 1.96 instead of the t-value that SPSS uses. Okay, so, but at any rate, the real lesson here is that you can do this for very large sample sets using SPSS, or you can do it by hand using the t-table. Okay, now, you can also get t-scores on Excel. Just like you can use normdist to get a t-score, to get normsdist or normdist to get the z-values, the values of the z-scores that you need using Excel. There's actually functions tdist and t-inverse, so on, that you can use to get the t numbers that you need on Excel as well. Or you can use the tables. Okay, so I think it's time for us to call it quits.